Hey folks, Professor Gray here, ready to talk to you again about confidence intervals. Now recently we talked about confidence intervals when you're finding an estimate for a proportion. How about when you're finding an estimate or an estimate for a population mean? Well, to do so when sigma, that's the population standard deviation, is known, then we take x bar as our point estimate, that's the sample statistic corresponding to what we're estimating. Subtract the margin of error to get the left bound, add the margin of error to get the right bound, and the margin of error is calculated in a different way because of the type of confidence interval this is. The formula for margin of error, capital E, is Z sub alpha over 2, that's the critical value for the confidence level, times sigma, that's the population standard deviation, divided by the square root of n, which is the sample size. So we are strictly talking about scenarios in which we know the population standard deviation. That's why sigma is in the formula. If we don't know sigma, then we'll have to do something different, and we'll talk about that a little later on. Notice also in the notation I have the lower bound less than mu, less than the upper bound. The less thans and mu stay in the answer. Mu is what I'm estimating. It's what I'm trying to find a range for. Here's an example. A simple random sample of 75 birth weights in the U.S. has a mean of 3,433 grams. The standard deviation of all birth weights is 495. We'll find a point estimate for the population mean of all birth weights in the U.S. Use a 95% confidence level and find the margin of error. Construct a 95% confidence interval for the population mean, and then we'll interpret the confidence interval in context. So for number 13, we're finding the point estimate, and the best point estimate for a population mean is the sample mean. In this problem, the sample mean is 3,433. Done. That's my point estimate. If I can only pick one number to estimate the population mean, that's really the best one I've got. Well, now we'll find the margin of error, and we have a formula for that. It was on the previous slide. All right, so the common critical value, well, hopefully common, the critical value times the standard error of the mean. First thing to substitute in is Z sub alpha over 2. Well, this is a 95% confidence level, and 95% is a common confidence level. If we look to the common critical values portion of the positive z-score page down at the bottom right hand side, I see that my critical value is 1.96. For sigma, that's the population standard deviation, I look back at the scenario in the problem, and the standard deviation of all birth weights. Now I know that this is a population standard deviation because of the word all. Standard deviation of all birth weights. That tells me that this is a population parameter. So sigma is 495. And the sample size, well, there were 75 birth weights in this sample, so 75 is n. And I'm going to put some parentheses around that fraction or rational part of the formula. And if I do that, I can type that into the calculator just as it appears. And I get my margin of error as 112 point, well, we'll round this one to 2 decimal places, 0.03. That's my margin of error. Number 15 says to combine and make a 95% confidence interval. All right, to make a confidence interval, for the lower bound, we take x bar and subtract off the margin of error. For the upper bound, we take x bar and add the margin of error. We already know x bar and the margin of error. We just substitute those in. And I get my bounds. I leave in the less thans and mu, and I have my confidence interval. Another way I can write this confidence interval is in interval notation. Like that. It looks like a point, but it's actually an interval. The less thans are illustrated in interval notation by the use of the curved brackets. If those were square brackets, they would be less than or equal to's. One way that you should not write this is by combining the two notations. Do not do that. That's incorrect notation. It muddles them up. Instead, one of the top two will be correct. And you should be able to recognize either one of them. Number 16 says to interpret the confidence interval. We would do so by saying that we are 95% confident that the mean U.S. birth weight is between 3,320.97 grams and 3,545.03 grams. That's using the template that was used earlier when interpreting confidence intervals. Again, we're 95% confident because it's a 95% confidence level that the mean, because we're estimating mu, that's the population mean, U.S. birth weight, because that puts it in the context of the problem, of the scenario, is between the lower number, 3,320.97, and the upper number, 3,545.03 grams. Well, let's make that confidence interval, or find that confidence interval one more time. This time we will use the calculator in its entirety. To use the calculator to find confidence intervals for the mean when sigma is known, that's the population standard deviation, we will use stat, test, and z interval. Z is in zebra. I go to stat, test tab, scroll down to number 7 on mine is z interval, and I have some things to fill in. Now if I have a list of birth weights instead of having the summary statistics, I would go to data and press enter, and then I would put in my population standard deviation, tell the calculator which list I'm using, use the number 1 for frequency, put in my confidence level and calculate. In this particular problem, I have stats. I have summary statistics. So I go to stats, make sure it's highlighted, and now I've got to fill those in. Sigma is the first thing I fill in. That was 495. X bar is the next thing, 3,433. N is the number of birth weights, that's 75, and C level is confidence level 0.95. Once all of those are filled in, I calculate and I get my answer. Rounded to the nearest whole number, our answer is the same as the calculator's. The calculator shows it in interval notation. It also reminds you of X bar and the sample size. So that's how to find a confidence interval for a mean when sigma, the population standard deviation, is known.